Okay, right. So we have about 15 minutes in which I want to go back and discuss the exponential map and the idea of a one parameter abelian subgroup, okay?
Sir, I had a question on the compactness of parameter.
Yeah.
So if there is R1, so that is not compact because it is infinite.
Yeah.
And a circle is finite. So what if the circle is like a Mandelbrot fractal line that has infinite length, but it can be seen from like a circle, but it has infinite length because of the fractal thing.
Right. I mean, so a fractal line is something that has say infinite length, but it is like wrapped up in finite volume, right? So you know, kind of I think there are all this. Hilbert has one, you know, all kinds of stuff. Space filling curves, right? They're known as space filling curves. So you know, we are not interested in the embedding of that line within a higher dimensional manifold here. What we are interested in is, you know, whether, you know, that line is finite or infinite. So, you know, if you take an infinite line like an R1, so it goes all the way, and you want to think of it as a space filling curve, something like this. You know, I don't remember, but you know, you have some volume, but you have some you know, non-intersecting curve, like the curve that Hilbert invented or some other mathematician invented. You know, it doesn't matter if I'm, you know, I can still kind of, you know, use one parameter to parameterize that whole curve, right? It's just that in its embedding in a higher dimension, it looks like, you know, whereas, you know, these 2 points are far away here. But, you know, when you do a space filling curve, then suppose that these 2 points get mapped to these 2 points, right? So in this embedding, these 2 points are nearby. But if you still think of the parameter in the curve, they're still quite far away. So I'm not so much interested in how it is embedded in a higher dimensional manifold. And that's so basically...
It will still be infinite. I mean, it will still be non-compact.
Yeah, I mean, it is a non-compact. Even here, it is non-compact. But what it is that its fractal dimension is different. So fractal dimension is essentially measuring how much of the higher dimensional space is this thing kind of occupying in some rough sense, right? And that's, you know, well, there's a rigorous definition of a fractal dimension. And so we are not interested in the fractal dimension here, okay? So we are dealing with continuous things, you know, and these are interesting questions. You might be able to come up with some notion of groups where a more fractal idea of a parameter is appropriate, but that is beyond the scope of this course.
Okay, sir, got it.
Okay, okay, all right. So let me talk about the exponential map. So now suppose we are given a Lie algebra element M, then one can exponentiate, you know, it M to generate a finite element e to the power I alpha m for some finite number a alpha. So this is a finite element of the Lie group G, right? So this map, which is exponent, it's a map from the Lie algebra to the group, is called the exponential map. And this map depends on M, right? It's called the exponential map. Okay, so explicitly, the exponential map takes an element of, yeah, sorry, let me just note. Yeah, it depends on the element, right? So it takes M to some exponential of I alpha M, okay? So the exponential map has the following properties. Number one is that if the parameter is 0, then we just have the identity element, okay? Or maybe just like, because it's a more general thing, let's write it like this, okay? Number two is that, okay, I'm just gonna write over here, not I, but yeah, don't worry about it. Yeah. And the other thing is that, well, there's a problem I have, because over here I'm using the same notation as here. Whereas, let me just use a different kind of notation. So let's call it tilde. So the exponential map has the property that if the parameter is 0, then we just get the identity element. The other property of the exponential map is that if I take some generator M and multiply it by some number S, some parameter S, and then multiply like the product of two exponential maps with the same generator, gives me this. So, and hence, the exponential map generates a one family, one parameter family, I should say. So one parameter, the alpha is the parameter, family of a one, not family, a one parameter Abelian subgroup of G. Okay, so because this means that because we are adding this and addition of these parameters is commutative, that means that this property means that the this composition law gives me, along with this guy, these two guys give me an abelian subgroup. And number three is just that if I take the derivative of the exponential map with respect to the parameter, and then set the parameter to 0, then we get back the Lie algebra element. Okay. So this is an example, the definition of the exponential map and the definition of one parameter abelian subgroup of G. Now let me give you an example.
Sir, this exponential map, is this just E or anything to the power Tm would do?
Sorry, anything to the power T?
Exponential is natural E.
Right. I mean, yeah, I mean, the thing is that because you're dealing with matrices, you have the exponentiation has to be defined in terms of a power series. So yeah, as long as you can define it as a power series, that's fine.
Okay, sir, got it.
Right. So you know, what do you mean by say 2 to the power m, where m is a matrix, right? Whereas the meaning of the exponential of m when m is a matrix is pretty clear.
So this exponential map is just E, the constant E. Okay, sir, got it.
Yeah. Okay, so as an example, let's take the group SU2. Then the Lie algebra G tilde is SU2 tilde, right? And the Lie algebra of SU2 tilde is the generators are tau 1, tau 2, and tau 3. And they have, we know that tau I is half times the Pauli matrices. Now let's take tau 3, which is half times 1, 0, 0, minus 1. Then the exponential of some parameter times tau 3 is going to be e to the power I t by 2, e to the power minus I t by 2. Right? And this you can show it's isomorphic to E1, right? Just for this parameter, and this parameter, because it's an exponential, t will be between, say, 0 to 2 pi, with these 2 points identified, right? So, so this is a, you know, so all these matrices, they form a one parameter subgroup, which is U1. Now, as an exercise, and I want you to do this, show that, say, T3, so T2 and T3 also form one parameter subgroups. One parameter subgroups under the exponential map. So this is your exercise. Okay, so I think I'm gonna end here, but because it's midterm, we can blah, blah, I'm not gonna take attendance. But if you have any questions, let me know, and but the class is officially over.
Sir, I have a question on the matrix representation of SO3 and SU2. So I saw that sometimes they are expressed in numerical terms like I00 I or something like that, and sometimes they're represented with cos theta, sin theta, minus cos theta. So how does this number and trigonometric function represent the same group?
Yeah, that'll be a question in your second assignment.
Sorry, sir.
You'll have to. That'll be a question in your second assignment, which will be deployed in a day or two.
Spoiler.
So, yeah. But no, good question. Yeah. Yeah, I mean, but you know, I can say something like, for example, here we have T, right? And you know that these guys, right, this is exponential of something. You can use the Euler formula here, right? If you use the Euler formula, then you can express this in terms of sines and cosines.
So the map takes some representation of SO2 to some representation of SO2, another representation.
I mean, these are not representation. This is the defining representation. This is not a different representation. We have not talked about the representation theory of SO2. SO3 is a representation of SU2. That's true. But you know, SU2 can have an infinite number of representation, and we will talk about that. That will be one of the fundamental results of representation theory. And if you've done quantum mechanics, you've seen that before. When we derive the representation of the angular momentum algebra in quantum mechanics, that is identical to the representation theory of SU2.